Today I want to spend a few minutes with you talking about EMC and EMI standards in automotive, and specifically susceptibility. The first use of a semiconductor in an automobile was actually for the rectification of the alternator. So previously to this time period, the alternator wasn't an alternator at all. It was a dynamo. It was a DC generator. And the reason for moving to an alternator was performance. Power requirements had increased on vehicles, and dynamos were notorious for not working very well at low RPM. During this entire period through the 70s, 80s, and 90s, we had the rapid development of microcontrollers, microprocessors. So if you go back right around towards the end of 1970, we had the first ABS systems being demonstrated by the likes of Chrysler, Daimler, Ford, all had kind of competing systems. And then as more and more electronics started appearing in vehicles, you had things like the CAN bus. So again, towards the end of the 80s, the first CAN bus IC chipsets became available. And then towards the end of the 1990s, we had onboard diagnostics for the first time. And what was fairly revolutionary at the time is that was mandated in the United States to have a common, basically fault-finding interface to the vehicle. Obviously, a lot has happened since then. There's a lot that happened beyond the year 2000. We have autonomous driving, self-driving, infotainment. But I want to kind of go back to the 80s and 90s a little bit, because this is the period where these electronic systems like ABS and so on first started appearing in what I would consider mass market vehicles. And I'm going to give you a couple of examples of why EMI matters. And that's really the purpose of this intro and focusing on this is, why does EMI matter to an automobile? So ABS was introduced in the first sort of mass market vehicle by Mercedes in 1978, their S-Class, their premium vehicle. But there were some issues. So the vehicle would be driving along happily along the road, and the ABS would malfunction. So the brakes would be applied, accidents occurred. And what it was traced to was there was a particular stretch of Autobahn that had a transmitter alongside the Autobahn. And what was happening was that radio transmitter was impacting the ABS electronics that were inside the vehicle. The solution to that was, or a temporary solution, was a metal grid as a shield was actually erected alongside the freeway to attenuate the field from this transmitter. So that's the first example of a real-world impact of EMI on a subsystem inside a vehicle. The other example is one I actually experienced personally. It was the early 90s, late 80s, early 90s, and I was picking up a colleague from London Heathrow Terminal 1. And if any of you are familiar with London Heathrow Terminal 1 at that period, then you may remember that as you pull up to the terminal, there is a radar tower that is directly next to where you drop off and pick up passengers. So on top of this radar tower, there's an antenna array, and this is rotating roughly once every 20 seconds. And it's sweeping a roughly 2.7 gigahertz shaped radio beam out to pick up vehicles, aircraft, air traffic, and so on. So what that means is if you're in your car picking up a passenger or dropping one off, that radio beam gets swept across that vehicle every 20 seconds or so. So I knew that was happening because every time the radar beam went round, the radio station I had listened to, the music, would just get converted to a buzzing sound as the radio beam went past, and then when it went away, the music would come back. I happened to notice on my right-hand side, because I was stuck waiting for the traffic to move, I was surprised because the gentleman next to me, his windows were going up and down. I was thinking to myself, why is he doing that? And then I realized his vehicle was actually stopping and he was restarting it, and he had that look on his face of what is going on. And then I made the connection, because every time I heard the buzz as the radio beam got swept over my vehicle, his car would act crazy. So this is another real-world example of where radio interference can have a negative effect on the operation of a vehicle. You can clearly see that if EMC can cause misoperation, there are definite safety hazards. So what I want to talk about next is, what did the industry do about it? So clearly something had to be done to make sure vehicles didn't have any misoperation or safety-related issues when exposed to radio frequency interference. So with that knowledge, and with the standards bodies like SAE, ISO, the automotive companies got together and created specifications that components had to meet in order to be considered and to be safely used inside an automobile. So you might expect that this would be done well. One simple way of doing it would be, okay, I take my car and I put it in an anechoic chamber and I blast it with radio frequency interference. And that is actually one of the tests that are performed today. The whole vehicle is subjected to a range of radio frequency interference. But this is a very kind of cost prohibitive way of doing the testing, because you've got the full vehicle. If you find problems, then it's very difficult to change. So it's actually broken down into subsystems. So yes, the car is tested, but so are the individual subsystems inside the vehicle are tested in isolation. But then individual components, like an IC, are also exposed to a variety of radio frequency interference tests. And that's what I'm going to talk about next in relation to Power Integration's products. So Power Integrations provides AEC Q100 qualified products. But over and above that, we test susceptibility and immunity and radiated levels that come from our devices. So what I have here, it looks a little strange. We have the device. This is an inner switch on one side of the board, and we have the rest of the power supply components on the reverse. And this particular configuration is designed for measuring the radiated noise that is actually being generated by the device. This is placed into a GTEM cell, which you can see on the screen. And what's nice about the GTEM configuration is we can run that both ways. We can both measure the noise coming from the device and provide that data, and we can also inject radio interference into the GTEM cell so that this part is exposed to high RF fields. There are many configurations that actually the part goes through. So the GTEM cell is also anechoic chamber testing, and there's a bunch of other testing that we perform, fast transients and so on. So do you remember the problem at Heathrow that I mentioned from the late 80s, early 90s? Let me show you part of a typical auto manufacturer component specification. So this is the test levels for a component in volts per meter versus frequency. There's a typical baseline expectation of 70 volts per meter for a component, but there are a couple of spikes that are a couple of higher levels that are included. Can you guess what they are? It's very interesting. One of them is for radar, and where the level is increased to 150 volts per meter. And one of them is for cell phone. So by testing a component at these levels, we can guarantee that when the part is integrated into a module inside the vehicle, that there will be no difficulties with passing this kind of testing at the system level and then ultimately at the vehicle level. And why is that important? Well, it really comes down to two things. One is risk, and the other one is time. Developing vehicles is extremely expensive, so minimizing risk minimizes cost of development, and minimizing time also minimizes the cost of development. Well, thank you very much for watching. I really love this stuff. I hope you found this interesting. If you are interested in more information about how we do our testing, please come and visit us at power.com.